Ever feel like you're trying to crack some kind of secret code when you read about research studies or, see data presented everywhere?
Yeah, I think a lot of people feel that way.
You're definitely not alone. But understanding these fundamental ways research works, the core methods, it isn't just for academics in ivory towers.
Not at all. It's really a powerful toolkit.
Right. It helps anyone make sense of all the information flying around, make better decisions, whether it's at work, personally. And let's be honest, it helps you spot when someone's maybe trying to pull the wool over your eyes with some shaky numbers.
Absolutely. And that's what we're diving into. We've sort of synthesized insights from a whole lot of material notes from many sessions.
Yeah.
Looking at a real spectrum of research methods.
So think of this as your, streamlined guide.
Exactly.
Yeah.
A guide to grasping the key principles behind, credible research.
Perfect. So this deep dive, it's really focusing on how we get from those real-world puzzles, people often call them management decision problems or MDPs, how researchers turn those into focused questions we can actually dig into and learn from. Our goal today is really to equip you with a much clearer picture.
Yeah, how research is structured, the different ways you can work with data, and crucially, how to make sense of what it all means without, feeling totally overwhelmed.
Okay, so where does this whole research journey actually kick off?
Well, it almost always starts with a practical challenge.
Yeah.
A real issue that an organization or maybe a community is grappling with. That's the management decision problem. The thing out there in the world that needs a solution.
Okay, so hang on. It's not just some theoretical question somebody cooked up in a lab. It has to be tied to something real.
Precisely.
Yeah.
It needs that real-world anchor. The research problem then kind of grows out of that MDP. It's a more defined, more academically framed version of that initial practical issue.
I see.
And from that research problem, you then formulate very specific research questions. Those are the exact things the research will try to answer.
So it's like zooming in, going from a general feeling that, sales are down, to asking really targeted, measurable questions to figure out why they're down.
Spot on. And a really crucial point here is that the research should always feed back into solving, or at least informing, that original management decision problem. It's about relevance, rigor, and impact.
Right, not just research for the sake of it.
Exactly. It shouldn't just be an academic exercise.
That makes total sense. So, okay, who actually needs these answers? Who benefits from the research findings?
That's a great question, and identifying the stakeholders early on is critical. It could be managers needing to make strategy calls, or policymakers drafting regulations, maybe even customers affected by a product.
So knowing who it's for helps keep it focused.
Absolutely. It ensures the research stays relevant and that the findings actually get used.
All right, so we've got the problem framed, specific questions, we know who cares about the answers. Now we get to the bit that often feels a bit intimidating. Analyzing the data, what kinds of tools are we talking about here?
There's quite a range, actually, each with its own strengths. For people comfortable with coding, RStudio is, incredibly powerful.
RStudio, right.
Within that, you've got RScript for just writing and running code, and then RMarkdown, which is fantastic for creating reports that mix your code, the output, and your explanations all together. We even looked at a specific package, SAT2, useful for some initial explorations.
So RStudio is the coder's choice, really flexible.
Definitely. If you want maximum control and flexibility and you're okay with code, it's the way to go.
But what if you're, not a coder? What if you prefer something more visual?
Yeah, good point. That's where tools like Orange are great. It's got this drag and drop interface, super intuitive for people who want to process and visualize data without writing a single line of code.
Drag and drop, okay.
We even saw an example using a housing data set. You could literally click to import data, connect boxes to visualize it, and then export the results, say as a CSV file. It gives you this nice visual workflow for quick exploration.
That sounds much less daunting. And wasn't there another one? JASP.
Yes, JAFP. Just another statistical program that's a GUI-based tool, so a graphical user interface. Very user-friendly.
Like menus and buttons.
Exactly.
Yeah.
You import your data, maybe a CSV, then use drop-down menus to run all sorts of analyses, basic descriptive stats, t-tests, even regression. It's really handy for quick, exploratory data analysis EDA. Just getting a first look at your data, and for running hypothesis tests quickly.
Okay, so different tools for different needs or comfort levels, but underneath it all, what are these tools actually doing statistically? What are the core ideas?
Well, at the heart of a lot of this are some fundamental probability distributions, and interestingly, they often link back to the normal distribution, the classic bell curve.
Ah, the bell curve.
Right, so think about the Z distribution. We use that typically when we have a large sample size, and this is key. We actually know the standard deviation of the whole population we're interested in.
Which isn't always the case, right?
Often not. And that's where the T distribution comes in. We use the T distribution when we don't know the population standard deviation, especially when we're working with smaller samples. It looks similar to the Z, but it has slightly fatter tails.
Fatter tails, meaning?
Meaning it accounts for the extra uncertainty that comes from not knowing that population standard deviation and having less data. It's a bit more conservative, acknowledging we know less.
So Z is for when we're pretty confident about the big picture. T is when we have a smaller slice and need to be a bit more cautious.
That's a really good way to put it. Then you've got the chi-square distribution. That's often used for testing ideas about population variance, how spread out the data is, or for looking at relationships between categorical variables, like comparing frequencies across different groups.
Okay, variance and categories. And the last one, F.
The F distribution. This pops up a lot when comparing the variances between two or more groups. It's fundamental to ANOVA analysis of variance.
ANOVA, right, for comparing means across several groups.
Exactly. And the F distribution is also key in assessing how well a regression model overall fits the data.
Okay, so these distributions are like the mathematical foundations. How do we actually use them to test a specific idea? Like, is group A different from group B?
That brings us to parametric tests. These are statistical tests that make certain assumptions about your data. A common one being that the data roughly follows a normal distribution.
Okay.
The Z-test is one, as we mentioned. Then there are several kinds of t-tests. There's the one-sample t-test. Is my sample's average different from some known value?
Like, is the average score in my class different from the national average?
Perfect example. Then the paired samples t-test compares averages from two related groups. Think before and after measurements on the same people.
Ah.
And the independent samples t-test compares averages from two separate unrelated groups.
And that's the one we used in the Boston housing example, wasn't it? Comparing house prices near the Charles River versus those not near it.
Exactly. The CHS variable was ERO for not adjacent, one for adjacent.
Yeah.
We used an independent samples t-test to see if the average house price, MEDV, was significantly different between those two groups.
Right.
And we touched on the difference between students' t-test, which assumes the two groups have similar variability or variance,
Okay.
and Welch's t-test, which is more flexible because it doesn't make that assumption. So if you're unsure if the spread of price is the same in both groups, Welch's is generally safer. But the core question is the same. Is there a difference in the mean price?
Makes sense. And what about the chi-square and F tests in this parametric context? You mentioned variance.
Yeah, so the chi-square test we talked about can be a one-sample test of variance testing a hypothesis about the spread in a single group. The F test, besides its role in ANOVA, can be used to specifically test if the variances of two populations are equal. That can actually help you decide whether to use the students or Welch's t-test we just discussed.
Ah, okay, so they connect. Now, whenever we talk about tests, these terms null and alternative hypothesis always come up. Can we break those down simply?
Absolutely. Think of the null hypothesis, HA, as the default assumption, the status quo idea. It basically says nothing interesting is happening.
Like no difference, no effect.
Exactly. No effect, no difference, no relationship. So a null hypothesis might be, this new drug has no effect on blood pressure compared to the placebo. Or the average commute time for people using route A is the same as for route B. It's the baseline assumption of nothingness.
The boring option, kind of.
You could say that. The alternative hypothesis, H, is what the researcher usually suspects is true and is trying to find evidence for.
Okay.
It states that there is an effect or a difference or a relationship. So the alternative would be, the new drug does affect blood pressure, or the average commute time is different between route A and route B.
Got it. Null is no change. Alternative is something's going on. Crystal clear. Okay, let's shift gears to regression. That word alone sometimes sounds, well, complex.
It can seem that way, but linear regression is actually a really useful and common tool. It helps us understand how one or more independent variables, the predictors, relate to a dependent variable, the outcome we're trying to explain or predict.
Like in the example where we tried to predict house prices. MEDV, using crime rate, Sharma, and maybe at the age of the building, AGE.
Exactly that example. You're modeling how changes in crime and age are associated with changes in median home value.
So when you run that analysis, what are the key numbers or results you should look for?
There are a few main things. R-squared is a big one. It tells you the proportion of the variation in your outcome variable, like house prices, that your predictor variables collectively explain.
So a higher R-squared means your model explains more.
Generally, yes. A higher R-squared suggests a better fit, that your predictors account for more of the story. Then there's the ANOV table for the regression. Yeah. That includes an F statistic and a p-value, which tell you if your overall model, all predictors taken together, is statistically significant. Does the model as a whole actually explain more variation than you'd expect by chance?
But what about the individual predictors? Like, is crime more important than age, or vice versa?
Great question. That's where you look at the coefficients for each predictor. And crucially, you often look at the standardized estimates, sometimes called beta coefficients.
Standardized estimates, beta.
Yeah. These are calculated after standardizing all your variables, putting them on the same scale, usually with a mean of 0 and a standard deviation of 1. This standardization lets you directly compare the strength of different predictors.
Ah, so it levels the playing field.
Exactly. In our housing example, the standardized coefficient for crime rate might be, say, -0.5, while for age it's -0.2. Even though they're measured in totally different units originally, the betas tell you that relative to their own variability, crime rate has a stronger negative punch on house prices than the age of the housing stock does.
That's incredibly useful. So you can actually say, okay, this factor seems to have a bigger impact than that one. It helps with interpretation, right?
Yeah.
And figuring out what really matters.
Precisely. It moves beyond just saying it's significant to understanding the relative importance, which is huge for drawing meaningful conclusions and potentially contributing to theory.
Yeah.
But interpretation isn't always straightforward. Mm-hmm. One common headache is something called multicollinearity.
Multicollinearity. Okay, that sounds like a mouthful. What is it?
It basically happens when two or more of your predictor variables are highly correlated with each other. They're moving together too closely.
So they're kind of measuring similar things.
Often, yeah.
Oh.
This makes it really difficult for the regression model to untangle their individual effects on the outcome variable. It's like they're stepping on each other's toes.
And we saw this potentially with the NDUS variable in the Boston data, the proportion of industrial land.
Yes, that was a prime example. NDUS on its own might show a reasonable correlation with house prices. But when you throw it into a model with other variables, it's likely correlated with things like pollution levels, NOx, property tax rates, TACs, percent lower status population, LSTAT, distance to employment, DS, maybe even AG.
Things that also relate to urban density or maybe blight?
Exactly. When those are all in the model together, NDUS might suddenly look statistically insignificant. Its p-value might shoot up.
But why, if it correlated decently by itself?
Because its explanatory power overlaps significantly with those other variables. They're all explaining a similar chunk of the variation in house prices. This redundancy inflates the standard error of the NDS coefficient,
making it harder to be statistically significant.
Right. The estimate becomes less precise, less stable. It's like trying to figure out which of three people singing the same note loudly is really responsible for the sound. You can even get weird results called suppressor effects, where adding correlated variables can actually make another predictor seem less important or even flip the sign of its effect.
Wow. Okay, so predictors being too similar really muddies the waters. It makes it hard to trust the individual results for those variables. So what can researchers do about this multicollinearity mess?
Well, one powerful technique is principal component analysis, or PCA.
PCA.
What PCA does, essentially, is it takes your original set of correlated predictor variables and transforms them into a new set of variables called principal components that are deliberately constructed to be uncorrelated with each other.
Uncorrelated? How does it do that?
It finds linear combinations of the original variables that capture the maximum possible variance in the data, with each new component being orthogonal statistically independent from the others. So you end up with these new uncorrelated components that summarize the original information.
And then you use those in the regression instead.
Exactly. You regress your outcome variable onto these principal components. Since the components aren't correlated, poof, no more multicollinearity problem in the regression step itself.
That sounds clever. But wait, these components are mathematical combinations, right? How do you even interpret what they mean? They're not crime rate or age anymore.
That's the tricky part. And it's where something like generative AI can actually be surprisingly helpful.
AI?
You look at the loadings, basically, how much each original variable contributes to each new principal component. You can feed these loading patterns into a Gen AI model and ask it to suggest a semantic interpretation, like a meaningful name or theme for that component.
Seriously, like give it a name.
Yeah. For example, if a component is heavily loaded with high values for industrial land, pollution, tax rates, and maybe negatively loaded on things like good schools or distance from the city center, the AI might suggest calling it something like urban stress factor or industrial burden component.
Whoa, that's like putting a human understandable label on a complex statistical pattern.
It really is. It helps translate the numbers back into concepts we can grasp and discuss. The AI can provide contextual explanations, maybe even draft narrative summaries of what these components seem to represent, helping you build a story around your findings. Of course, you always need to sanity check it with your own expertise.
Okay, that's fascinating. So PCA transforms the variables first. We also mentioned something called regularized regression ridge, lasso. How does that tackle multicollinearity?
Right, regularized regression takes a different tag. It works directly within the regression estimation process itself. It adds a penalty term to the equation.
A penalty? For what?
A penalty that discourages the coefficients of the correlated variables from getting too large. It essentially puts a constraint on them.
So it's like reining them in, preventing any one of them from dominating just because it's correlated with others.
Exactly. Ridge regression applies a penalty that shrinks the coefficients towards zero, making the estimates more stable, especially when multicollinearity is high. It keeps all variables in, but reduces their influence.
Okay, it shrinks them. What about lasso?
Lasso regression is a bit stricter. Its penalty can actually shrink some coefficients all the way to zero.
So it does variable selection too. It kicks some predictors out.
Effectively, yes. If a predictor isn't adding much unique information, lasso might just eliminate it from the model. ElasticNet is kind of a hybrid, blending of penalties from ridge and lasso. The overall goal is more stable, reliable models, particularly when predictors overlap.
Got it. So regularization directly controls the coefficients during model fitting. Now, how does that compare to something called filter-based feature selection? Is that similar?
Not quite. Filter-based feature selection is usually done before you even build the main model. It's more of a pre-processing step.
Okay, how does it work?
It looks at each predictor variable individually and scores it based on its relationship with the outcome variable, maybe using a simple correlation or an F-score from a quick univariate regression. Then it ranks the predictors by their scores and just keeps the top ones, filtering out the rest.
Ah, so it judges each predictor on its own merits in isolation.
Exactly. It doesn't consider interactions or overlaps between predictors. It's fast and simple, which is an advantage.
But the downside?
The downside is it might miss predictors that are weak on their own, but powerful in combination with others. And critically, it doesn't directly address multicollinearity. It could easily select a bunch of highly correlated variables if they all individually score well against the outcome.
Right. So it might pick redundant features. That's a key difference from regularization, which handles the redundancy during the modeling.
Precisely. Regularization methods look at the predictors together and manage the overlap. Filter methods look at them one by one beforehand. Different philosophies, different strengths and weaknesses.
Okay, that distinction is clear. So we've built a model, maybe dealt with multicollinearity. How do we know if the model is actually good? We mentioned R squared, but you implied that's not the whole story.
Far from it. There's a really critical difference between statistical significance and predictive accuracy.
Okay, break that down.
Statistical significance, which often focuses on p-values, is mostly about explaining relationships within the data you already have. Do we find evidence that this relationship likely isn't just due to random chance in this sample?
Right.
Predictive accuracy, on the other hand, is all about how well your model predicts outcomes on new, unseen data. It focuses on minimizing prediction errors and how well the model generalizes.
So a model could find statistically significant relationships in the current data, but still be terrible at predicting the future.
Absolutely. That happens all the time, especially if the model is overfit to the specific quirks of the training data.
Overfit. Okay. So how do we assess that predictive accuracy then? How do we know if it will work on new data?
A standard technique is k-fold cross-validation.
K-fold. Sounds like laundry.
Huh. Sort of. You split your data set randomly into, say, k equal parts or folds, often 5 or 10.
Okay. Then
you train your model on k1 folds, e.g. 4 out of 5, and you test its performance on the one fold you held out.
Right, the test set.
Then you repeat this k times, each time holding out a different fold for testing. So every part of your data gets used for testing exactly once.
I see. You rotate the test set.
Exactly.
Yeah.
Finally, you calculate your performance metrics, maybe root mean squared error, RMSE, mean absolute error, MAE, maybe even R squared on the test sets for each of the K-runs, and you average them.
Why all that repetition? Seems like a lot of work.
It gives you a much more robust and reliable estimate of how your model is likely to perform on genuinely new data. By testing on multiple different subsets, you reduce the chance that your performance estimate is just a fluke based on one particular train-to split. It helps guard against that overfitting problem.
Okay, so it's a more honest assessment of generalization ability.
Precisely. There are variations too, like leave one out cross-validation or repeated k-fold, but the core idea is the same. Test on data the model hasn't seen during training and do it systematically.
That makes a ton of sense. Okay, different topic shift. What if our predictor variables aren't numbers? Like, what if we have categories, say, gender or region or type of treatment? You can't just plug north or female into a standard regression equation, can you?
Correct. You generally can't. That's where dummy variable regression comes in handy.
Dummy variables. Okay.
The idea is to convert these categorical variables into a series of numerical 0, 1 variables. For a simple binary category, like gender, male, female, you just create one dummy variable. You might code female as 1 and male is 0, for instance.
So 1 means yes, this category 0 means no.
Exactly. Now, if you have a category with more than 2 levels, say region with north, south, east, west, that's K4 categories, you create K-1 dummy variables.
K-1. So 3 dummies for 4 regions, why not 4?
Good question. You choose one category to be the reference or baseline category. Let's say north is our reference. Then you create dummies for south, 1 if south, 0 otherwise, east, 1 if east is 0 otherwise, and west, 1 if west, 0 otherwise. The north group is represented when all 3 dummies are 0.
Ah, okay, so the coefficients on those dummy variables tell you.
They tell you the estimated difference in the outcome variable, like salary maybe, between that specific category, e.g. south, and the reference category north, holding all other predictors constant.
So it lets you compare groups within the regression framework.
Exactly. It lets you include categorical factors, compare group effects, and control for group membership when looking at other variables. Just got to watch out for the dummy variable trap, including all Ulukami's creates perfect multicollinearity, so always leave one out as the reference.
Got it. Always K1. Now, what if the relationship between 2 variables, say x and y, isn't fixed? What if it actually changes depending on some third variable?
Ah, now you're talking about moderation. Moderated regression is the tool for that.
Moderation.
It examines whether the relationship between an independent variable, x, and a dependent variable, y, is influenced by, or depends on, the level of a third variable, the moderator, m. It answers the question, does the effect of x on y change for different values of m?
So, like, maybe the effect of caffeine, x, on alertness, y, depends on how much sleep someone got the night before.
Perfect example. Less sleep, maybe caffeine has a stronger effect. To test this, you include an interaction term in your regression model.
Interaction term.
You literally create a new variable by multiplying x by m. If the coefficient for this interaction term is statistically significant, it's evidence of moderation.
Yeah.
The impact of x on y isn't constant. It varies depending on m.
And what's this idea of a pure moderator?
A pure moderator is a variable m that influences the x-y relationship only through that interaction term. It doesn't have its own direct separate effect on y.
So in our example, maybe time of day could be a pure moderator if it affects how caffeine impacts alertness, but doesn't directly make you more or less alert on its own, independent of caffeine, which might be debatable, but illustrates the idea.
Exactly. It only shapes the x-y link.
Yeah.
Now, this sounds similar, but is different from another concept, mediation.
Right. Moderator versus mediator. This always trips people up. How are they different?
It's a really key distinction. Think about the question they answer. A moderator answers when or for whom does X affect Y. It's about the conditions that change the relationship.
Okay. When or for whom?
A mediator answers how W or WHY does X affect Y. It explains the mechanism or the process through which X influences Y. The effect is indirect, flowing through the mediator.
How or why? Can we use that mentorship example again?
Sure. Mentorship, X, leads to career advancement.
What?
A mediator could be building professional skills. Mentorship helps you build skills, X mediator, and having better skills leads to advancement, mediator Y. The effect of mentorship on advancement happens through skill development.
Okay, that's the how.
Now, a moderator in that same scenario might be mentee proactivity. Maybe mentorship X has a stronger positive effect on advancement Y for mentees who are highly proactive. Proactivity changes the strength of the XY link.
Moderator. When or for whom, example for proactive mentees. Mediator. How or why, e.g. via skill building. That really clarifies it.
It's a fundamental difference. Interaction versus indirect effect pathway.
Are there specific tools researchers use for these since they sound a bit more complex?
Yes, definitely. The Hays process macro, which works with software like SPSS or R, is very popular. It automates the estimation of mediation, moderation, and even combined models like moderated mediation.
What's good about it?
It simplifies setting up the models, gives you clear output for the direct, indirect, and interaction effects, and uses bootstrapping, a resampling technique, to get more reliable confidence intervals for things like indirect effects, which can be tricky to test otherwise. There are also dedicated packages in R like mediation or Lavin that do similar things.
And just to make it concrete, we even brainstormed some potential moderators and mediators using the Boston housing data, didn't we?
We did, yeah, just hypothetically. For instance, could being by the river, CHAS, moderate the negative relationship between pollution, NOx, and house price, MEDV? Maybe the riverfront location buffers the price drop from pollution somewhat.
Okay, that's a when question.
Or could lower socioeconomic status, LSTAT, mediate the relationship between distance from employment centers, DIS, and house price, MEDV. Perhaps greater distance X tends to correlate with lower status areas, mediator, and it's this lower status that primarily drives down the price, Y.
That's a how-why pathway.
Exactly. Thinking about these potential roles helps build richer, more nuanced models of what's really going on beyond just simple direct effects.
This has been, wow, incredibly illuminating. Seriously, it feels like we've gone from the absolute basics of defining a research problem all the way to understanding these quite sophisticated analytical techniques.
Yeah, it's quite a journey, isn't it? From identifying that real-world issue, translating it into questions, choosing tools, understanding the core stats like distributions and tests, and then getting into regression as challenges like multicollinearity and these more complex models with moderators and mediators.
It really connects the dots.
And having that grasp, even conceptually, gives you such a powerful framework. It's not just for doing formal research. It's for critical thinking, for evaluating claims, for making better decisions based on evidence in, well, pretty much any part of life.
Absolutely. So for a final thought for you today, think about some piece of information you've come across recently. Maybe a claim in a news report, a statistic someone shared online, maybe the results of a workplace survey. Now, with this hopefully deeper understanding of research methods, how might you look at that information differently? What questions would you ask now about, say, how the data was collected, how it was analyzed, potential issues like multicollinearity or maybe even moderation? Could the conclusions be interpreted differently?
Yeah, it's all about taking these concepts off the page or out of the deep dive and applying them as a lens to the world around you. How can you use this to be a more critical, informed consumer of information?